Welcome all of you. Good evening, everyone. Good evening, everyone, and welcome all of you for today's live session, the Week 7 live session for Economic Operations and Control of Power System NPTEL course. Now, welcome you all. I'm Gagan Meena, a fourth year PhD student from IIT Bombay in Electrical Engineering Department, and my specialization is Power Systems. We will be following the same agenda which we have been following till now. We will go through the overview of week 7, then we will discuss some questions. In last, we will discuss certain questions. First, we will go through a detailed overview of week 7. And if you have any doubt, you can ask in between also and after the class also. So these are the deadline for the assignment 7 and 8. Tomorrow is the deadline for assignment 7, so please submit the assignment on time. And deadline for assignment 8 is next Wednesday, September 18th. And I hope all of you are able to access the live recordings and as well as the PPT PDF of these PPTs presentation used during these sessions. This is the link where you can get the recordings of live session, and the links for PPTs is available in the Google Drive. Link is available in the problem solving sessions tab on website. You can have a look. All the previous week recordings and these PPTs have been already uploaded. And these were the topics which were discussed in this week 7. The first thing was it was about the interchange. Till now, till week 6, we have been looking different methods of different control and operation methods, starting with the dynamic control in this AGC, automatic governance control, and group characteristics, all these things. We look area of the control error and all that. After that, we moved on to economic dispatch and unit commitment. We saw different methods of economic dispatch and also different methods for unit commitment like dynamic programming, then Lagrangian relaxation, which is one of the methods, one of decomposition techniques, one of the decomposition techniques. And economic dispatch also we have seen with and without losses. How to treat the loss function. Then we also saw this hydrothermal coordination. In the last week, we discussed the production cost model, which uses all these concepts. Previous all the previous used concepts. So here we are discussing how in a big interconnected system. First of all, we'll see why do we need an interconnection? First question is why do we need interconnection? What are the benefits for interconnecting? Hmm. Are there benefit of interconnection or interchange? Let me just connect the charger. So we'll just first thing is, are there any benefit of interconnection and interchange? If yes, then we have discussed what are those benefits. What are the different methods by which we can have interchange of power and energy, interchange of power between the interconnected areas. That we have to see ways of doing this, how to do all these things. This transmit, this title is it's coming from the previous week. The effect of transmission was to be seen here. We need to see that. Plus spot markets. So we'll see these are the different types of interchanges. The spot market is one of them. So we'll see power and energy interchange, then multiple utility interchange. Here the concept of wheeling comes up. Then we move to the effects of transmission, locational marginal pricing, LMP, and finally the spot market. We have spot market also. And that also we'll see how it works. All these things we want to address today in this week. And then last one was uh, problem. Uh, Numerical was discussed. So because you've already seen that, I will not discuss that numerical, and it's already available in the book also. But we will go through the concept, which is more important. But if you want me to discuss, we can discuss the numerical also. First, we will see yes why interchange is required. What are the benefits of uh, interconnection and interchange? If we have two areas, let's say area one, area two. This is area one, and this is area two. Both are independently operating. They have their own generation as well as load, set of generators as well as load. In between, they can have a transmission. They are connected. So there are several buses also. So different connections are there. Some network is also there. Okay. And loads are there. These areas are independently running. Independently, they are able to satisfy the demand. But if let's say there is some problem with respect to, there can be any kind of contingency. Let's say there is a uh, loss of load. Let's say one generator is out. One generation is on forced outage. Suddenly there is some issue or failure. Let's say turbine failure is there. One generator is out of operation. In that case, suppose the load in the area one was 700 megawatts and generation capacity, maximum capacity was let's say 1000 megawatt. Again, it was currently generating 700 megawatt to satisfy the load. But what happens? 500 megawatt generator, let's say 400 megawatt generator, it goes out of service. It is out of operation due to some forced outage. Then what will happen in this case? Now total available generation is 600 megawatt, which is less than the demand. And now demand is, we have already seen in week 1, if demand is less, demand is more than generation, then what will happen? Frequency will increase. Sorry, frequency will reduce. But however, if we have a interconnection between the area 2, let's say talk about area 2 also. Area 2 was serving a load of 1000 megawatt and it has a generation capacity of, let's say, 1500 megawatts. Okay, it can be less also. Now, area 2 is also able to meet the demand successfully. If these two areas are connected, then in case of this forced outage of 400 megawatt generator, what can happen is this load can still be satisfied. How? By an interchange of 100 megawatt from area 2 to area 1. In that case, load is in area 1 is satisfied or met. So frequency is under control, is at nominal. It becomes nominal in the steady state. There will be some transient because of the loss of generation. But after that, it will again be back to its normal value. So just a minute. Yes. So this is done. Yes, sorry. So load is met and frequency is under control. So we are able to increase the reliability of power supply. We are able to maintain the supply the demand even though there is a generation outage. So the interconnection results in an increased reliability. Another case is, so this is second point, the reliability enhancement. Then what we can have, suppose the generation was, let me rub this one. We saw that by interconnection we can have an increase in the, we can enhance the reliability or we can ensure the reliability, can ensure reliable power supply. Now what can happen, let's say this was area 1 or area 1 and this was our area 2, area 1 and area 2. Generation of 1500 megawatt and load demand of 1000 megawatt. Here it was 1000 megawatt and demand of 700. Now assume that although the generation here is more than the load in their respective areas, but there is one generator which is, let's say there are three generators here, A, B, and C. A has a maximum capacity of 400 megawatts, B also 400 megawatts, and C also C 200 megawatts. Here, let's say D, E, and F. Here we have a 600 megawatt, 400 megawatt, and this is 800 megawatt, and this is let's say 300 megawatts. And now cost-wise, if we see, this is rupees 2 per unit. This is rupees 7 per unit, and this is rupees 3 per unit. Just like this. It's just for unit. This is rupees 1 per unit, 1.5 per unit, and rupees 9 per unit. Now we can see here the generation is sufficient for area 1 to meet its demand. Similarly for area 2 also. However, the generator available in area 2 are costlier as compared to generators available in area 1. Now, area 1, there are two generators A and B which together meet a demand of 800 megawatt, and the demand is only 700 megawatt. Still, they have a 100 megawatt is still available. And here, if we see 800 megawatt, it can meet demand in area 2, plus we need 200 more. But since these two generators are cheaper, say the A is consumed, B in area 1, A plus B are supplying 700 megawatt. So what they can do, the remaining 100 megawatt they can transfer to the area A or area 2. Now what D plus generator B. D is providing 100 megawatt. Generator B will provide 100 megawatt, and because now this unit F is cheaper than the unit C, the F 100 megawatts from C can be used. Okay, so even if sufficient generation is there, that contingency cases, normal operation is there, still interconnection can make the operation economical. It can reduce the overall cost of operation. That's why you see, and finally we have already seen that frequency also can be regulated when there are changes in two areas, changes in overdraw of demand and frequency. Generation load mismatch is there in one area, then the other area can help to avoid, to correct that mismatch. Here you can see the advantages of interchange, interconnect is first is economics. So cheaper energy can be bought from the neighboring area. Then continuity of power supply in case of contingency. This increases enhanced reliability here. This is economic operation. And third one is frequency regulation. Interconnected areas can regulate frequency and respond to emergencies better than the isolated system. If we have an isolated system here, then the frequency dynamics will be poor. There will be a lot of variation around the nominals, and it may not be even, in this case, it is not even possible to restore the frequency back to its nominal value. The only solution would be to curtail the load, which is so load curtailment is always an emergency situation. We don't want to do that. We want to avoid that as much as possible. Now these are different interchange categories. How we can have these interchange between different connected areas. The first category is energy category. Here we have different, even in energy category, we have different types. We have these subcategories. One is economy A, which the example which we have already seen. Simply because of economic advantage, there can be interchange between area 1 and 2, just as we saw in the previous example. Simple, only because of economics. Now economy B is here. There was no scheduling of here in economy. There was no scheduling of power interchange. It was not scheduled, but it happened. But in B, we schedule the interchange power to optimize, further optimize by considering it, by modeling it in the unit commitment itself. The unit sales, this means that we buy those, we have area, same example, area 1 here, this area 2. So we had one large generator here with 800 megawatt generator, which was generated here in area 2. So the load serving entity here, entity in area A, can purchase a part of this, a portion of this large generator to import power and import power to the area 1 to supply the demand. This is unit sales. Then diversity. Diversity means that we are able to, the connection of two areas. Diversity is in terms of the peak load. If these two areas are having different load profile, especially the time of occurrence of the peak load is different. Let's say here the peak load is happening at 8 p.m. and here it is happening at 7 p.m. or even 7:30, maybe 9 also. But they are different. There is a difference of almost 4 time blocks here. One time block is of 15 minutes. The difference of 4 time blocks. Um, we can easily manage the generator which are used here, the set of generators which are used here to provide the peak demand. If here in area 2, because we already see area 2, the generation capacity is much more. And in area 1, if the peak, let's say the demand comes out to be more than the 700, more than 700, or there is outage and there is also demand more than the existing, which was 700. So suppose the forecast, so the actual demand is much more than the forecast. Then this area 2 can supply power here. So connecting areas with two different interchange with system having different time of peak day. In that way, both the areas will be able to meet their peak load because they are occurring at different times. So generating assets in one area can help to meet the peak load in the other area, and vice versa. For both the areas, it can happen. So in that case, what will happen? The actual generation available after the force outage and schedule maintenance, that area, let's say in area 2 at the peak hour, let's say at 8 p.m. in area 2, the actual load, actual demand is more than the actual generation. So this is more than the forecast. And this is even less than the forecast because of it is less than forecast. And there can be many reasons for that if we consider renewables also. Even if we have only conventional, then it might happen that there are force outage of generators. Then if renewables are there, then we have solar or wind. In that case, if let's say solar is already out, like 8 p.m. no solar, and wind output of wind is very less because of the high temperature in surrounding areas, so no pressure difference. So wind is output of wind generators is also less. So conventional is on force outage and wind output is also less. And let's say if storage is there and storage is not sufficiently charged, is not the charge in the storage is not enough, then we need power from the extra from the neighboring area. We need to import power. In that case, the area 1 can help to meet this peak demand at 8 p.m. Same thing is applied to, let's say, the, the storage here. It can be even more interesting. Storage here in area 2 is not able to meet the demand because say at 7 p.m. the area 2 helped area 1 to meet its demand by the storage discharged. The storage discharged to meet the demand in area 1 at 7 p.m. So now its state of charge is not sufficient to meet the entire demand, meet the entire excess demand in area 2 at 8 p.m. So it's a hypothetical case. It can happen also. It can happen, but generally we would like to, because it's uncertain. We don't know how much demand will be there, but still, in general, buffer will be kept in storage for, especially for the evening hour for ramping time. So this is a ramp up when the solar is going down. So this is ramping hours. The high net ramp is required from either gas turbines or the storage. Then a buffer would be kept ideally, but suppose in this case if it is not there, which can happen, the sufficient buffer may not be there as it was envisaged. In that case, we need to import power from area 1. Now area 1 can do that because here we see 8 p.m. the load is less in area 1. Hence very less. Let's say it is around average. It can easily supply. The area 1 can easily supply the load, the demand in area 2 at 8 p.m. So this is how the diverse area, when two areas with peak demand occurring at different time, they are connected, then they can help each other to meet their peak demand with a very high reliability. This is a very good use case of interchange or interconnections. And there are several interconnections between different countries. Now even India has interconnections with the neighboring countries in Bhutan, Nepal, and Bangladesh. We are in a process to have this interconnection with the Southeast Asian countries also, in Myanmar. You have heard about that one world, one grid, something like that. That is also, people are thinking about connecting different countries. Even in European countries, if you will see, you'll find several interconnections are there when, between Denmark and Sweden. We have one interconnect. Denmark has high wind penetration. Different characteristics of these countries, two areas can be met. Their diverse generation mix can help satisfy the diverse demand requirements. Because here in case of India, Bhutan and Nepal, they are hydro rich in hydro. Very high hydro potential and hydro generation mix. Their hydro generation is quite high in their overall installed capacity. When India has peak demand during that time, Bhutan and Nepal are able to supply demand, meet peak demand in India. And vice versa also, that is possible if they are available. If demand is there in Nepal and Bhutan, and if there is excess generation in Indian subcontinent, then that can also be used to supply demand in the neighboring countries. So it's a very good uh, example. Then next one is energy banking. It is generally it refers to banking. We already know the term bank where we store something, we deposit something and we use it later at a later time. Similarly, we can deposit the energy with this. It can happen. It's a contract between two generators. Generally, two different types of generators for and most commonly used between hydro and thermal. Because hydro might be generally we see thermal is more and hydro is less. In that case, if hydro, if the peak load is there and thermal is not able to meet, then thermal can deposit that energy in hydro and use it during the peak time. During off-peak hour, it can energy deposited with the hydro can be used in that case. deposit energy and withdraw it later without accounting for the sale prices. It usually occurs when a high storage capability hydro system is interconnected to a run-of-river hydro or thermal system. So when hydro input to the hydro plant is quite high, then it would want to sell it to the thermal. And the hydro may also want energy when it is during the low water time, when the water input is quite low. In that case, thermal can also provide energy to hydro. So instead of doing hour on hour basis of interchange or charging or transaction cost, usually they deposit a kind of energy. The depositor would deposit energy wherever it had a surplus, and only the megawatt hour deposited would be accounted for. And whenever the depositor needed energy, it would simply withdraw the energy up to megawatt hour it had in the account with the other system. Which system is banker or depositor depends upon the contract. The role may even reverse as a function of time. As a function of time in a year, the hydro and thermal can interchange the role. When the hydro has the next one is the inadvertent interchange. This happens when there is error in controlling interchange. Like AGC, we have already discussed these area control errors. When there is some error in these AGC system, or area control error is not um, it, we are not able to make it zero. Then this inadvertent interchange comes into action. Then last one is the take or pay. It is similar to gas contracts, which we have already discussed. Moving on to the next type of interchange. The next type of interchange we have is this dynamic energy, and there are two types are is one is jointly owned units and second is the remote delivery. Dynamic energy contracts, they change as a function of other flows. They change. That's why the word dynamic is change as a many when neighboring utilities find that demand growth does not justify a new power plant on their own, then a pool of owners is formed to build a new plant. And then one plant is operated by the agreed shares of unit with dynamic interchange across all the control areas to deliver generation from the jointly owned unit to the owner, as if the plant was in the owner's control area. One unit is owned by many entities, and this will generally be done when the cost of meeting demand does not uh, entail means when it is not economical to have a new plant to satisfy the demand. The cost of meeting the demand is quite low as compared to installing a new power plant. In that case, it is better to have such an arrangement where different entities can jointly share a plant and use them as per their requirements, share decided as per the contract. And similarly, one is remote demand. This the demand and changes in demand are the responsibility of a utility, not in the control area. After mergers or purchase of other utilities, a demand center can be isolated within another control area. So such a demand is the responsibility of serving utility. Third category is the contingent. This comes up during contingency. In that case, contingency, there can be faults in transmission line. There can be outages of generators or transformers or transmission lines. In that case, these interchanges will be required. One is the capacity. This is the capacity market where capacity is purchased. So another system can help cover the generation's capacity reserve. For any kind of contingency, the system is required to prepare itself for any kind of contingency. Generally, we consider n minus 1 contingency that out of n elements available in the system, if one element goes out, if that one element can be transmission line, it might be a generator. If any one element goes out, then will the system should be able to meet the demand as per the n minus 1 contingency criteria. Similarly, there can be n minus 2 or n minus k up, but as we go to as we increase k, then cost of maintaining these additional reserves also increases. The most commonly used is n minus 1, where we consider that the largest generating unit. We consider the outage of this. The system should be able to meet the outage of the at least it should be able to meet the output outage of the largest generating unit, and it can be as high as 1.5 gigawatts in a very big grid like Indian grid. In that case, if suddenly a 1.5 gigawatt generator, a supercritical thermal power plant goes out, or ultra critical power plant goes out, then a system should still be able to meet the demand. For that case, we require reserves. So one area can, if it does not have sufficient reserves, then it can contract additional capacity to maintain this reserve from another area. So this is capacity. Second is the emergency when there is a load curtailment. So to avoid the load curtailment situation, we can have some emergency reserves. Those can be used. Then spinning reserve in case of whenever there is some contingency. We apart from this capacity reserve, we also have these uh, on-bar spinning reserve. These are the generator which are already connected, synchronized to the system. That's why it is called spinning. They are running, they are generating. But they also have some limit. Let's say one generator is there, its capacity is 800 megawatt, but at present, currently, at T is equals to, so what is the right now? It is 6:45. Let's say 6:45 p.m. time block. From 6:45 to, let's say, this 7 p.m. Although this is the installed capacity of the generator, but the generator is only generating 600 megawatt, that it has a buffer of 200 megawatt, which is capped as a spinning reserve to meet any kind of contingency. But this generator can quickly ramp up. It can not quickly, but depending upon the ramping limits, it can gradually increase its output to 200 megawatts. So this is one generator, but there are many generators, several generators. Together they will have amount of spinning reserve which is required for the system, which is designed as per the design. It can be 5%, 10%, or just some percentage of the peak demand which is kept as a spinning reserve. Then we have ready reserve. These generators are not on, they are off, but they are ready to generate. Another system, so all these resources are available in the other area, not in the area where the demand is being met, but in the other area. So these are the generator which are ready to start up on a short not notice. So these are ready to start up on a short notice. Gas generators are a good example of these kind of users. Now even storage can be very quickly started. So it can quickly provide and quickly supply the need. Hydro is also another example. So here we can have hydro, gas. Quickly here, if we say, depending upon the frequency, here you want primary uh, frequency regulation, secondary or tertiary. We can use them. Since we want quickly do it, secondary is a secondary frequency regulation. The primary energy storage can be used, especially the is flywheel or the supercapacitor. Capacitor is can be very quickly they can discharge. Then next category is market-based transactions. In this case, we have the category demand side management. Part of the demand response where then Florida Energy Broker and market such as PGM. These two we will discuss in the subsequent slides. The next category is transmission line users. This also we will discuss in the next slide. These are the different methods because it's a we discussed that we want to if I have a let's say I have an optimal resource generating resource, I have a cheaper resource. The cheaper resource is there and also it is not at its maximum limit. Then technically it can provide out, it can meet the demand. Then economically also it can meet because it is very cheap. But if transmission line is not sufficient, the capacity, transmission capacity is already fully utilized. Then although the generation is cheaper and is available, to satisfy the demand. We cannot do that. So we need to ensure that the generation has sufficient transmission capacity available to satisfy the demand. And for that, we need to pay for the transmission capacity. We need to pay. And there are different methods uh, for this calculating the method. Different methods for transmission line cost allocation. These are different methods: postage stamp, dollar per mile, and jointly owned transmission. Now we will discuss these methods. And last in this category is the reliability. So this is the postage stamp method. This is the most simplest tariff, simplest method to calculate the transmission line usage cost. Simplest method. And it is called postage stamp method because it replicates the cost of sending a letter from one post office to another. Because it's always fixed, right? We go from one place to another. And it is no need in this method, no need to calculate transmission line flows. It is independent of transmission distance, supply and delivery points, or the loading on different transmission facilities caused by the transaction under study. That how we calculate the cost. In this case, first of all, the total cost of operating the transmission system is calculated for the year. And then the contract flows for each hour are divided by the expected contract flows for the annual period using the transmission system. This way we get a percentage which is multiplied by the total annual cost to find out the cost of each contract. It's a fixed number. That percentage is a fixed variable. And then, so it's a very simple method, but there are many problems with it. And it is independent of network itself. You cannot apply a blanket rule on any kind of transaction. It, it depends on the supply delivery points, because how the combination of supply and delivery points affects the flow on. Although there is a transaction between node A and node B, which are a part of a bigger network having several nodes interconnected with each other. Although there is a transaction between these two nodes, the power flow on other nodes are also affected. We need to take care all those things into account. So our megawatt mile method tries to do something close to that. It is called a line by line method. It takes into account the line flows. It considers changes in megawatt transmission flow and transmission line length. The flow as well as lines. Dollar per megawatt per mile. So if you this we know for each line, we know the cost of the line. We can multiply the transacted amount of power on that line and the length. And we can calculate the cost for that transaction. Sorry, there was big issue. I will just again share my screen. I hope it is visible now. Okay, so we're discussing the megawatt mining method. The line by, it is also called the line by line method, and it considers the changes in the flow as well as the transmission line length in the miles. But here the difficulty is to identify which contract use which transmission line. Elaborate techniques need to be used to keep track of these contracts and how each contract is affecting different transmission lines. So that we need to keep track of. The next point, important thing was the locational marginal price, which we will see again in the subsequent slides. Locational marginal price. So the cost of transaction by using LMP is very easy. Let's say there is a transaction between node A and node B, or node I, bus I, bus J. Then from OPF we can calculate the, for economic dispatch we can calculate the LMP at each bus LMP, and then just take a difference. Let's say X megawatt or is PW megawatt is transacted from I to J. Then the cost of transaction will be LMP I minus LMP J. Now, next concept is when there are multiple entities, multiple utility transaction. In that case, the concept of wheelings comes into picture. And in simple words, it is a use of some parties' transmission line for benefit of other parties. The use of someone's transmission asset for supplying demand. That is a wheeling of power. It takes place when there are multiple utility interchanges. Let's say there is a transaction from A to C, and it's an interconnected network where A and C are connected to other nodes also. But then right now the transaction is happening between A to C. Okay, although this transaction is happening between A to C, but there will be the effect of it will be seen on other interconnected lines as well. You can see here this 100 megawatt from A to C is going in so many ways. So first this 100 megawatt is dividing into 50 megawatt. So if we see, although we were transmitting 100 megawatt directly between A to C, only 50 megawatt is flowing between the line connecting A to C. The rest is coming from through different other routes, from other routes. So here this 100 megawatt first divide itself into 50 megawatts. Then it again divides into 25. And this 25 and this combines to give 50 and this goes here. So many parallel paths are there, loops are there. If it's a purely DC network and if you ignore losses, then the same 100 megawatt will reach here. But if we consider the losses, then it might happen that the losses in these parallel paths, in these loops, can be, yeah, they will be certainly more. If you transfer 100 megawatt, then less than 100 megawatt will reach because there are losses in all these lines. So these losses also need to be taken into account, and the supplier need to supply more than 100 megawatt, and the cost of loss will also add into the cost of transaction between A to C. So yes, although transaction is there between A to C, but all other interconnected areas are affected. So what is the problem here? Problem is there can be increased losses in the system due to interchange, due to this transaction. Then another thing is the parallel path flow. They utilize the capacity which was supposed to be utilized by the wheeling utility. Although we wanted this 100 megawatt to reach from A to C. If we have, let's say we have only one line. If we had only one line, but we know that interchange is very important. We cannot have a single line for reliability and for economics and for frequency regulation. We need other lines. We cannot avoid that. So even if we had only one line, then entire 100 megawatt and very few, let's say, loss was only 1%. So 99 megawatt would reach here. Or we would have to transmit 101 megawatt and 100 megawatt we will get here. But now, even though we transfer 100 megawatt, inject 101 megawatt from A, here we will not get 100 megawatt because there are losses in all these lines. So that's why these power flow utilize the capacity which was utilized, which was supposed to be utilized by the wheeling utility. Although it was supposed to utilize the 100 megawatt, but it is not happening. Here is the next concept, next thing which we discussed was next topic was the power phases. Now we have discussed that we need interchange. We have already seen different types of categories of interchange. So many categories, and all these are contracts. Now, so many demand, several thousands of or even lakhs of demand serving entities are there, load serving entities are there. Similarly, thousands of generators are there, and on daily basis, on hourly basis, for each hour, for in future, for next 1 year, they have planned, they have contracts. If we keep on making such contract between thousands of entities, they so much is a cumbersome process. It is like marketplace, it becomes a marketplace. So to make it organized, sometimes these entities are created which are called powerful companies. They will work as a central dispatch office to ensure economic benefits. So overall, there is a benefit to everyone. They try to do that. Their aim is to optimize or to maximize the economic benefits, and in that pursuit, they also do achieve other benefits also, like maximizing the economic benefits directly results in minimizing the operating cost, or indirectly it's a result. When we try to minimize the operating cost, it will maximize our economic benefit. And perform the central dispatch office it also performs a system-wide unit commitment. So all these things the central dispatch office tries to achieve. It can do all these things. It performs a system-wide unit commitment. Try to minimize the reserve being carried throughout the system. So if we have a central dispatch office, we can do so many things. Individual will not do a unit commitment thing. He will not perform a system-wide unit commitment. He will perform their individual area-wise, but system-wide unit commitment will be performed by the central dispatch office. Then it will also take care of the reserves which are required for the overall system basis. Then it will maximize the benefits of emergency procedures. Then it will coordinate maintenance scheduling also to minimize the cost and maximize the reliability by sharing reserves during maintenance period. All these things can be done by the central dispatch office. Then, although so many things can be done, but there are certain disadvantages also, like because it's a central dispatch office, we need an entire infrastructure of for communication, better control and coordination. Then complexity of arrangement is quite large. It's a huge, very complex arrangement is required for that. And then additional costs on a recurring cost of supporting these interutility structure is required to manage and administer the pool. Dedicated IT infrastructure is required. Communication, two-way communication and computation facilities are very, because it's a central dispatch office and thousands of generators and load serving entities there in bilateral contracts, multilateral contracts are there. A very huge, a good computation facility is also required. Its maintenance is required. Then operating and investment costs associated with all these offices and its paraphernalia is required for that. Uh, Once this is done, uh, the central dispatch is done, then the next thing is to allocate the pool saving between the entities. This pool saving allocation can be done in two ways, two methods. There are other methods also, but these are the two uh, common methods. This is after the fact. One is real-time mode, so doing the allocation on hourly basis or whenever the transaction is taking place at that time. Then next one is after the fact computation, after the transactions. In real-time mode, the cost and saving allocation are made periodically using the incremental and decremental cost of the system, and power is sold to and purchased from the pool, and participants' account are updated currently. The account are also updated on a real-time basis. However, here the computation first it will not happen in a real-time basis. It might happen on a interval basis. So here computation of first of all the individual pool member cost, they will calculate their own production cost as if they were operating just to serve their own individual. Then the savings are calculated as a difference of the sum of all these participant own load cost and the actual cost determined by the pool dispatch. Then that saving is allocated according to the rule which are designed or decided by the pool. So this is, as we saw, that one of the interchange category was as this market based. Market based. Now we are moving to this market based. First one we discussed this. Now we are moving to this Florida energy broker. It's a market based interchange category. So what is this? It is a central broker. It accepts quotation to sell and quotation to purchase, and then it it facilitates by creating an orderly marketplace where demand, supply, and prices are known simultaneously. So what is done here? Each member on an hourly basis, it will transmit an incremental cost and the number of megawatt hour or a block it is willing to sell. Similarly, or the same entity can also have the decremental cost. The other entity can have decremental cost and number of megawatt hours or the block it wants to buy. So generally, load will do this and generator will do this, but some entities which are uh, in between, they can do they can do both. And they can buy from the market and then sell to the load. They can do that. Um, Morgan and Stanley is one such company which does that. Now how transaction is done? It the broker will match the lowest cost seller with the highest cost buyer, proceeding in this manner until all offers are processed. So the matched buyers and sellers will price a transaction on the basis of rules established in setting up the broker scheme. And one of the rule commonly followed is the split savings model. So this is the split savings model. Here Fs is the incremental cost of selling utility and FB is the decremental cost of the buying utility. And FC is the cost of transaction. The cost of transaction is equals to the incremental cost of buyer plus the difference is shared between both the entities. So half FB minus FS. So this will be half FS plus FP. That means the transaction cost is the average of the seller's incremental cost and the buyer's decremental cost. Now we'll move to the next topic, which is the transmission effects and issues. So we have transmission. We started with the interchange. Interchange is needed for that we need transmission capacity, sufficient transmission capacity. But transmission capacity has limits, on the technical limits, how much power it can transmit, and which is governed by several constraints. One is thermal limit. So many limits are there. One is thermal limit of the transmission line because of the amount of current they can carry. The larger the current, larger the amount of current, larger will be the loss. And the loss, size per hour loss, will produce heat. And if the temperature is quite high, then the conductor can even melt. In that case, it will be permanently damaged. We don't want to exceed that thermal limit. We never want that. Then there are also transient the stability limit. We have seen this P delta curve. Stability delta also we cannot increase beyond this. But if we know that P is equals to V1 V2 by X sine delta. If we have one generator here and one generator here, or even if we consider it as an infinite bus, it is one angle 0 and this is, let's say, this is some, this is V1 angle delta. Then this becomes V1 by X sine delta. And in general, if we have, let's say this is V2 angle 0, then it will become V2 even V2 by X. The power transferred over this line will be V1 V2 by X sine delta. X is already fixed when the transmission line is erected. We cannot change that. V1 and V2, we try to maintain it close to 1 per unit. This is also, they are also very close. Can't do much about that. The thing which we can change is sine delta. Here we can change the delta. We can increase the delta, the power will be, and maximum power will be at delta is equals to 90 degrees. But we know that we cannot have delta at 90 degree. As soon as there is some perturbation, any fault, then because this is an unstable equilibrium, if we go here, then it will become unstable. System will become unstable, so we cannot do that. We cannot afford that. So we try to keep delta between 30 to 40 degrees. So that also that results in the stability limit, transient stability limit. We have this first contingency limit, that is n minus one contingency criteria. So if one transmission line goes out, then other transmission line also, they should be able to carry the power. Otherwise, load will be curtailed. Then we have voltage and VAR limits. These we voltage also we cannot. It's 0.95 to 1.05 per unit. The voltage also has to be kept within the limit, and for that we need to have reactive power support. And because of the thermal limit, we cannot. There is a limit to the reactive power which can be supplied carried by the transmission line. And when there is an outage, based upon the line outage, every utility has an or a system has to maintain this reliability. They have reliability. These are reliability metrics. These are measures to ensure that the system will be reliable under these outages or any kind of emergency situation. To keep these metrics as within acceptable range, we keep these reserves. So although contingency is there, if reserves are there, we'll be able to meet these levels. Otherwise, we'll not be able to do that. So we want to ensure that the LOLP, loss of load probability, expected energy, expected unserved energy. This is in megawatt hour. This is magnitude of the energy shortfall. In 1 year, how much load in megawatt hour will be curtailed as per the design, system design which we have, the reserves which we have, install capacity that we have. Based upon that, considering the forced outage rates and scheduled maintenance, what will be the expected unserved energy in megawatt hour for 1 year? That is given by expected unserved energy. Similarly, the number of let's say events, if we considering one time block as one event, so that will be event 15 minutes. So how many event 15 minutes? Summation of such divided by total number of events in a year. Total number of such 15 minutes blocks. In 1 day we have 96 blocks, and sorry, in one, yeah, 1 day we have 96 blocks, and in 1 year we have 365 days. So 365. The sum of event 15 minutes. For how many such 15 minutes time block there was load curtailment, or load curtailment can happen, which we permit. So what, as per our design, how much are we uh, willing to tolerate? The sum of all those time blocks divided by total number of time blocks. So this will be a percentage. This ratio will be it will be less than 1. If you multiply it by 100, then you will get percentage. LLP is measured in percentage, and also sometimes it is in loss of load expectation. It is in 1 day in 10 years. In percentage, it will be if you want to convert, it will be 1 divided by 10 into 365. It is 0.00023274. But this is the ratio, and if you, the probability will be 0.00274%. This is the LOLP standard which is kept. Okay, then we discuss the flow gate. Yeah, to ensure that the lines are within limit, we need to ensure that we need to take care that any transaction which we are allowing, which the pool or the central dispatch center is allowing, that transaction should not exceed the available capacity. After considering all the existing scheduled transactions, any additional transaction should not exceed the thermal limit, these limits. For that, we calculate this total transfer capability, available transfer capability, and we have this term called as flow gate. What is flow gate? It is it flow gate monitors the flow on a single or multiple transmission. It monitors flow on single or multiple transmission elements, and these transmission elements can be transformer, transmission line, or generator. So one flow gate can monitor one element or more than one element, and these are monitored under two scenarios. One is normal condition when there is no contingency. In that case, and for this we use these power distribution factors we use. And without contingency, it is called as the power. The distribution factor used is power transfer distribution factor, and with contingency, it is the outage transfer distribution factor. Using these factors, we can see that if 1 unit of 1 megawatt of transaction happens between two nodes, how that 1 megawatt is going to alter the flows in the entire system. So these distribution factors will quantify the incremental impact of power transfer on a flow gate or a particular transmission path, and it is expressed as a percentage. I think in the next week we will see how to calculate this PTDF and LODF or OTDF. And they are identified by different some methods that we'll not go through it. And this is the available transfer capability formula, where ATC, the available transfer capability, is equals to TTC minus TBM capacity benefit margin, and this transmission reliability margin minus ETC. FC is the available flow gate capability. It is a megawatt transfer capability on a flow gate that remains available for additional transmission service above and beyond the already committed and approved usage of transmission system. It is the additional that remain available for additional transmission service. Before approving any transaction, we need to check whether there is available transmission capability or not. If it is not available, then we cannot approve that transaction cannot be approved. It's very important to check to ensure that the system is operating in its normal condition. Otherwise, there will be load curtailment. Will not be able to, because uh, we cannot exceed these limits. We cannot violate these operating limits. We need to satisfy all the limits, and for that, only the available capacity can be the transactions equivalent to those available capability can only happen. Then this capacity benefit margin is the amount of firm transmission transfer capability preserved by ISO for load serving entities to enable access by entities to get generation from interconnected areas to meet generation reliability requirements. So all these three they are required for stability, reliability, and previous commitments. Okay, now we will move to the spot market, the last topic, and it's a very interesting topic. If we So market is something where someone has something to sell, and someone someone else wants to buy that. It's a place where buyers and seller can do a transaction. In electricity market, we have spot market where we can do transaction, we can buy or sell the energy for each time block. We have loads and we have generators. The load wants to buy energy, generator wants to sell energy. And they both these buy and sell bits, they are incorporated into the optimal power flow to model an auction. And then that OPF is used within a unit commitment block to schedule generation. Now there are two cases. One is when the load is inelastic. The load is inelastic, that means whatever the price is, the load remains constant. The load serving entity is willing to pay any amount of price to satisfy the demand. Inelastic, so it doesn't want to change the load requirement based upon the price. Generally, what will happen if the price is high? Everyone has a willingness to buy something. If you want to buy energy, and that depends upon the budget also, and the utility which is derived from buying that product. If a person is hungry, then he can eat 4 chapatis. But after eating those four, his willingness to eat one more will be less. Even if we, so he will not be willing to pay a huge amount for that one additional chapati. So a hungry person would want to pay anything to eat initial 4 chapati. But for one additional chapati after that, he is willing to pay very less. That is why the curve for the load serving entities is a decremental curve. This is the price and this is the quantity. So as the quantity increases, the price, the billing, the price he wants to buy at, price that he wants to pay for that is very less. That will reduce. So this type of curve is called elastic because it depends upon the price also. Let's say if the price is very high, one may want to avoid that. One might have a budget constraint. One might not be able to. One may not be willing to pay a very high price for meeting the load. It might happen that that load requirement is not that load is not essential load. Let's say the load may be non-essential, and curtailing that may not be a big issue. Not be a big problem. So the load serving entity or distribution company, DISCOM, might be unwilling to buy that electricity, that energy at a very high price. And on the other hand, let's say it depends upon the let's say city like Mumbai, where we want to supply, especially in the core city, the main city. We want to ensure 24 by 7 power supply. And to ensure that we need to have sufficient amount of uh, capacity and energy procurement from the market if required. So for that, the company would be willing to pay as high as a price to ensure that reliability is standard. And for that, they will charge the consumer also more than what is charged in the outskirts of Mumbai. So it's a the more reliable we want, the more the entity is willing to pay. Similarly, so this is the case for the demand utilities. On the other hand, the generation would want to quote a lower price so that his offer is accepted. Also, the new machines, they are efficient. Their cost of production, incremental cost of production is low. That company, generating company would want to use that first so that its profit is high. And as the capacity is utilized and the older units with a higher incremental cost are added, and the overall cost of production, the incremental cost of production, that increases. That is where the supplier or the generator has an incremental cost and the demand has a decremental cost. So this is a generator. And in between, you can see some point at some point the two can intersect each other, and that point is the point where the market is cleared. You'll also see that the same thing we are now trying to do it mathematically. So we saw, yes, we were discussing about the inelastic and elastic load. This one is the elastic load, the decremental, the load with the decremental curve. But if the decremental curve is like this, it's parallel to y-axis. That means whatever may be the price, regardless of the price, the load serving entity wants to meet this demand. That is the inelastic case. In that case, the load is constant regardless of the price being charged. In that case, the objective function is to minimize only the cost. Only generator bits are involved in the objective function. It becomes a cost minimization problem. If elastic load is there, then there is a worth function for this type of decremental cost, and the price of load serving entity, it provides the price the entity is willing to pay to purchase a amount of load Pj. In this case, the objective function is this Fi minus Wj Pj. It can also be written as maximize WJPJ minus FIPL summation. In this, if written in such a form, it is called as a social welfare maximization problem. And if we minimize the negative of it, then it becomes the same. Maximization can be turned into minimization problem. So we just multiply it by negative, and here we are minimizing the negative of that social welfare, the objective function. The problem formulation is very simple. Here we are minimizing this. So this problem formulation is for a single load, single generator system. Load and single generator system to make it easy to understand. Only one generator, one load is there. And here this is objective function, and we have only one constraint that the load should meet the supply should be equal to the demand. And now if we use a Lagrangian function, then we have this objective function here, fx plus lambda times g of x. And now if we differentiate it with respect to both the variables, which is pgen and pload, then we will get this. The incremental cost of generator plus lambda is equal to 0, and the decremental cost of load minus lambda is equal to 0. The solution is this: when the two curves intersect, that is the solution. That will be the market theory. So for a single generator, it is something like this. There is the incremental cost of generator, the incremental cost of demand. This is demand or load, and this is our generator, cost of generator. And this solution points to this point. Says that where the two curves intersect, that is the point of solution. That is a market clearing. So this will tell us this is the price here and this is the quantity here. This is the market clearing volume and this is the market clearing price, MCP and MCD. So the point of intersection of these two curves will be the solution here in this case. The same thing which we discussed, now we have also proved mathematically. Here you can see these are it's an example. Here we discuss only a single generator, single load example. This is example for 3 generators and 3 demand. And they have a stepped incremental and decremental curve. So this is buyer 1, buyer 2 and buyer 3 in different colors, red, blue and green. And these are seller 1, 2, 3. Now we can stack these steps of incremental curve and decremental curve one by one on increasing, stack these generators offer in increasing order to get an overall incremental curve, and stack these buyers bid in decreasing order. After doing this, we will get this curve. So here, if we see the seller 1 is willing to sell 700 megawatt hour, 700 megawatt hour per hour, a block of 700 megawatt hour at a price of $3 per megawatt hour. Similarly, this seller 2 is willing, it has a stepped curve. So for first 300 megawatt, he is willing to sell at $5 per megawatt hour, and next 400 megawatt hour, the generator 2 is willing to sell at $6. Similarly, other that G3 also. And if you take buyer one, then buyer one is willing to pay $10 per megawatt hour for first 400 megawatt, and after that it is willing to pay less. Overall, we get this curve. Overall, these are the demand bids, stacked in decreasing order, and these are the supply offers stacked in the increasing orders. And the point where they meet, the intersection point is, this is the intersection point, and this is called the, here we get the total volume which will be cleared in the market. So a demand of 1600 megawatt hour will be cleared, and these two, this demand, this red one is not cleared. So this one, this buyer one will only be able to get 400 megawatt hour. Similarly, this generator is also this G1 at 7 megawatt. The generator, only this generator is not scheduled, which is this one. The G3 will be able to sell only 200. Remaining 300 G3 is not able to sell. If this happens and there is no network constraint, then this price is applicable throughout the network. All the generators will get a payment of this $7 per megawatt hour. Now all the loads will have to pay same $7. So this area under this curve is called the demand surplus, and this is called the producer's surplus. Sorry, opposite. This is called demand surplus, and this is called producer's surplus. And the sum of two will be equal to the social welfare. The total area under this curve is the social welfare. If there is some bottleneck, some transmission line hitting its limit, in that case, the volume which will be shared will be less. Right? Let's say this, only this much is transmission capacity is available. In that case, the price increases. It becomes around 8.9. This difference is extra because of 9. This difference, it will be used to pay to the buyers of this FTR, owners of FTR, those who want some transmission rights. This surplus can be used to supply them. We will see here interpretation of bus lambda. So lambda is the price at each bus. These lambdas are the price at each bus, and they correspond. They are the locational marginal price. The generators are paid the LMP at the generator bus, and load must pay LMP at the load bus. And if there is no condition, both these values will be same. At all the buses we have same. And that will be same only when there is uh, there are no losses. So lambda is the instantaneous price of the next small increment of load. It is the instantaneous price of the next small increment of the load. And generator are paid the LMP at generator bus. Load must pay this LMP at the load bus. And DC power flow without congestion, then all the LMPs are equal, and there will be the total the payment received from load and the payment made to generator is same. The net will be zero, and the market operator collects from load and pays to the generator. And during congestion, the lambda is higher, and there will be surplus. And independent generator, and the surplus is the basis. That surplus is the basis of making payments to holders of contracts for transmission access. That surplus will be used in this way. Then an independent generator can purchase an FTR as an insurance policy against the possibility that the transmission system will not allow a desired transaction from a point of delivery to a point of receipt. The generation can buy a financial transmission right to ensure itself that whatever may be the situation, I will be able to deliver my power in the network. So it's an insurance to the generator. So if the capacity is not available, then still the generator will be paid. Okay, so I hope the things are clear. Now we will move to questions. What is the primary? The first question is, what is the primary purpose of interconnect and interchange in the power system? We discussed three main advantages. One was economical. Second was reliability, enhance reliability, and third one was frequency regulation. So what are the options? To facilitate energy transaction between power system, to regulate transmission use transactions, to optimize the operation of power pools, to enhance the security of power system. The primary purpose of interconnect is first one, to facilitate energy transaction between power system. And when this transaction happens, we have all these benefits also as a result of the transaction. Second is, which of the following is not an interchange category? So we saw different interchange categories. Let us revise them. The first one was energy. Second one was contingent was third one. Second one was dynamic energy. Here we saw jointly owned units and remote loads. Here we saw economy A, economy B, unit sales, and at emergency, inadvertent take or pay. or diversity in energy banking. You can say. Then the third one was contingent. Here we saw emergency capacity, then spinning reserve and ready reserves. Then fourth one was market based transactions. Here we saw spot market, Florida energy broker, and demand side management. Fifth one was transmission line use. Here we saw different method of cost allocation, transmission line use, postage stamp method, megawatt mile method, and jointly owned transmission lines. Then we also saw the wheeling associated problems. And last one was the reliability. So now we can easily check which one is not here. Dynamic energy is there, market is there, transmission is powerful transaction is not an energy. It's not an interchange category. So D is the answer. Then what type of transaction are involved in energy market? We already in energy markets. In energy market, we can have dynamic energy transactions, market-based transaction, and spot market transaction. So all of these are correct. What is the locational marginal pricing used for? This is the fourth question. First option is to calculate TTC, total transfer capability. Then to determine transmission use transactions. To cost the transmission use based on location. This is not correct. To evaluate economic interchange now that we can do without LMP also. So LMP is used to calculate to determine that. So what is the correct answer here? To cost the transmission use based on location. Because this is bus dependent, we already seen. For each bus, we will get one LMP. It will be used to. But TTC we have already seen. ATC is equals to TTC minus. Calculation of TTC depends upon the available capacity in the transmission line. LMP is associated with pricing, not the capacity in transmission line. So this is not correct. And these LMP are derived after from this transaction. It is not that the transaction are done based on LMP. It's why otherwise. When transaction is there, the result is LMP. Then what is the main disadvantage of operating power pools? We discussed disadvantages. Limited transmission capacity is not capability is not uh, related to this. Complex coordination and allocation process is correct. Then high costs associated with interchange. Lack of control over energy transaction. Which one do you think is the main disadvantage? Complex coordination and allocation system, right? Lack of control, how lack of control? It will have no control. High cost, we saw that power using powerful results in more economic benefits. How can we say high cost are associated with interchange? Then next question is how are the savings allocated in power pool? And that also is right. FBFS, it is buyers decremental cost, sellers incremental cost. Buyer, sellers incremental cost. and the transaction cost was seller's incremental cost plus divide the savings between the two. Then this becomes average of the incremental cost of seller and incremental cost of the buyer. So this is the transaction cost. A proportional, the savings are allocated in a power pool proportional equally between supplier and area receiving pool energy. Equally, that is why it is half year. That is why it is half year. What is the role of energy broker in the power system? To regulate transmission use transaction, to facilitate energy transaction between power system, to allocate savings in the power pool, to evaluate economy interchange. Which one is the correct? To facilitate energy transaction. These three things are done by power pool, central dispatch center. The broker is just providing a facility for them to come and do a transaction. What is the problem associated with parallel path in wheeling? It results in inefficient transmission use. The capacity which was supposed to be used by wheeling utility, that is being utilized by the parallel paths now. That is the problem. What is the purpose of identifying flow gates in power system? To calculate the transfer capability. You already say that flow gates are they monitor the flow over one or more than one transmission element, and transmission element are elements can be transformer, transmission line, and or it can be a generator also. Okay. And we saw flow gate can be independent, calculated by this distribution factor. There are two types of distribution factor for transfer. This is without contingency. This is in case of contingency. This is for normal operation. Last question, what is the role of spot market? To facilitate energy transaction, to optimize power generation schedule, to regulate energy transaction, to evaluate economic interchange, to facilitate energy transaction. Yeah. So we'll stop here. Thank you everyone for joining today's session. We'll meet again next Tuesday. Thank you very much.